Alright, let's continue. Let me open the table of content. Okay. Okay, if I remember correctly, we are in this section. Let me check that. Okay. Let's take a look at the fork system call. This one. And also wait. Also exec. Right. Okay. Alright, let me okay. I'm kind of curious about the call stack. Like we are using the array of character, which, if I understand correctly, was stored in the call stack instead of the heap or memory or dynamic memory. So, are we using the same call stack when we are using exec? That's kind of interesting. I mean, if we didn't use the same call stack, this pointer would become dangling pointer, I guess. Yeah, I'm not really sure. Maybe one day we will understand. But yeah, this is kind of interesting of a question, at least for me. Okay, this is the motivation. We're splitting the API into fork and exec to create new process. And then we already tried this one, right? Figure 5.4. Okay, we already checked this one too. Is to send signal to a process, pause, and not useful imperative. For convenience, in most Unix shell, certain stroke combinations are configured to deliver a specific signal to the currently running process. To interrupt, Ctrl-C, dan Ctrl-Z to, what is it, suspend, maybe that's the word, the TSTP, and then you can submit later with command, the FG command. The entire signal subsystem provides a rich infrastructure to deliver external event to process, including ways to receive and process the signals within individual process, and ways to send signals to individual. Okay, this is about the main page, right? Okay, this is the new term process group, which currently I have no idea what this means. Like, how do we grouping the process? Something like that. There is this form of communication. The process should use the signal to call to catch various signals. Doing so ensures that when a particular signal is delivered to a process, it will suspend its normal execution and run a particular piece of code in response to the signal. Okay, this naturally raises the question, who can send a signal to a process and who cannot? Generally, the system we use can have multiple people using them at the same time. If one of these people can arbitrarily send signals such as SIG-IN to interrupt a process, like terminating it, the usability and security of the system will be compromised, right? As a result, modern systems include a strong conception of the notion of a user. The user, after entering password to establish credential, logs in to gain access to system resource. The user may then launch one or many processes and exercise full control over them, pause them, kill them, etc. Users generally can only control their own process. It is the job of the operating system to parcel out resource, such as CPU, memory, and disk, to each user and their process to meet overall system goal. To parcel out resource. Okay, and then there's these useful tools. There are many command line tools that are useful as well. For example, using the ps command allow you to see which process are running at the main page. Okay, in case anyone new, you can do something like this to check the manual for the main page. System manual pager. But keep in mind that the main command itself needs to be installed. On Arch Linux, it was the package called MainDB, if I understand correctly. But on another Linux distro, you need to check that yourself. Okay. Some useful fact to pass to PS, so we can check the main page of PS or the manual page of the PS like this, main PS. Then we can get the information of it. And also we can check how many manual sections we have by using this F flag like this. Okay, we have this one and this one. The P1, the P in here usually means POSIX section. If we do something like this, we are in the POSIX programmer's manual instead of the general command manual like this one. So there is a little bit of information. For some useful flag to pass to PS, the tool top is also quite helpful as it displays the process of the system and how much CPU and other resource they are eating up. Humorously, many times when you run it, top claims it is the top resource. Oh, perhaps it is a bit of an egomaniac. Okay, I didn't realize that top claim it is the top resource. Okay. Interesting. Perhaps it is a bit of egomaniac. The command kill can be used to send arbitrary signals to process, as can the slightly more user-friendly kill all. Be sure to use this carefully. If you accidentally kill your window manager, the computer you are sitting in front of may become quite difficult to use. Okay. Yeah, the window manager. Okay. Finally, there are many different kinds of CPU matter that you can use to get a quick glance understanding of the load on your system. For example, we always keep menu meters, okay, from matching many software, okay, running on our Macintosh. Okay, I mean, yeah, I don't use Mac and never use one, so I have no idea what this is. So we can use how much CPU, we can see how much CPU is being utilized at any moment in time. In general, the more information about what is going on, the better. The summary, okay. We have introduced some of the API dealing with unique process creation, right? The unique process creation for exact weight. However, we have just skimmed the surface, okay? Only the surface. For more detail, read Stephen and Rango. Oh, of course, particularly the chapter on process control, process relationship, and signal. Okay. Now, even process have relationship, to keep that in mind. There is much to extract from the wisdom therein. Okay, Stephen and Rango. We will take a look at the reference after this one. I assume, like this one, the reference. Okay. While our passion for unique process API remains strong, we should also note that such positivity is not uniform. We should also note that such positivity is not uniform. Okay, for example, a recent paper by System Research from Microsoft, Boston University, and ETH in Switzerland that there's some problem with fork, okay, and advocates for other simpler process creation API, such as Pound. Do we have that? Nothing. Okay. Read it and the related work it refers to understand this different vantage point. Well, it is generally good to trust this book. Remember too that the author have opinions. Those opinions may not always be as widely said as you might think, right? This is the subjective aspect of the book. This opinion. Okay, wait a minute. Let me read this. A system generally needs a user who can administer the system, the administrator, some people say, and is not limited in the way most users are. Such a user should be able to kill an arbitrary process. Example, if it is abusing the system in some way. Even though that process was not started by this user, such a user should also be able to run powerful commands such as shutdown, which unsurprisingly shut down the system. In Unix-based systems, these special abilities are given to the super user, the root, right? Usually the super user called root. But yeah, maybe in other system they call it using different name. But in Unix-based system, we usually call it root user, something like that. The special abilities are given to the super user, sometimes called root, while most users can kill other user process. The super user can. Being root is much like being Spider-Man. Okay. With great power comes great responsibility. Thus to increase security and avoid costly mistake, it's usually better to be a regular user. If you do need to be root, tread carefully, as all of the destructive power of the computing world are now at your fingertips. Okay. Right. Okay, aside key process API term. Each process has a name. In most systems, that name is a number known as a process ID or process identifier, usually abbreviated to PID. The fork system call is used in Unix system to create a new process. The creator is called the parent. The newly created process is called the child. As sometimes occurs in real life, the child process is a nearly identical copy of the parent. Not the exact copy, but near identical. The wait system call allows a parent to wait for its child process to complete execution. The exec family of system calls allow a child process to break free from its similarity to its parent and execute an entirely new program. And this what make me curious. When we are using exec system call, are we using the same call stack that the process that the process create, or we are creating a new call stack? Yeah, I'm still not sure about that. Again, an entirely new program. So maybe the call stack also bound to the process rather than the program. Maybe I'm still not sure. A Unix shell commonly use fork, wait, and exec to launch user commands. Okay, the separation of fork and exec enables features like input or output redirection pipes and other cool features without changing anything about programs being run. Process control is available in the form of signals, like the control C, the interrupt signal, which can cause job to stop, continue, or even terminate, right? Which process can be controlled by a particular person is encapsulated in the notion of a user. The operating system allows multiple users onto the system and ensure users can only control their own process. Like, I think it was called isolation, maybe something like that. So we isolate each user that are using the system. User can only control their own process. A super user can control all process and indeed do many other things. This role should be assumed in frequently and with caution for security reasons. Okay? I don't want someone who using my server to suddenly interrupt my my process, right? Let's say I submit a report and then suddenly someone else abort the process of me submitting the report. That would be bad. A fork in the road. Oh. A fun paper full of forking rates. It to get an opposing viewpoint on the unique process API present at the Always Livelihood OS workshop, where system users go to basing extreme opinions in the hope of pushing the community in new direction. Oh, I didn't know there is system researcher. Okay, interesting. And there is a workshop too. Okay, a multiple Processor System Design, an early paper on how to design multiprocessing system. Maybe the first place the term fork was used in the discussion of spawning new process. Okay. Programming semantics for multi-program computation. Okay, a classic paper that outlines the basic multi-program computer system undoubtedly had greater influence on Project Magmatic and eventually Unique. Okay. Programming semantic for multi-program computation. They could be twins. What? The hard-hitting piece of journalism shows a bunch of weirdly similar chat or parent photos and is frankly kind of mesmerizing. Is that how you pronounce it? Okay. Mesmerizing. Go ahead. Waste a minute of your life and check it out. Okay. But don't forget to come back here. In this in microcolumns is the tangent of surfing the web. The tangent of surfing the web. Okay. Hints for computer system design. Okay. Lamson's famous hint on how to design computer system. You should read it at some point in your life and probably at many points in your life. Oh, okay, interesting. With great power comes great responsibility. The code investigator concludes that the earliest mention of this concept is 1793 in a collection of decrees made at the French National Convention. The specific code to even what is this language? French. Is this French? I don't understand. Which roughly translates to they must consider that great responsibility follows inseparably from great power. Only in 1962 did the following words appear in Spider-Man. With great power there must also come great responsibility. So it looks like the French Revolution get credit for this one, not Stanley. Sorry, Stan. Okay. Advanced programming in the Unix environment. Oh, okay. That's Stephen Rango. Nuance and subtleties of using Unix API are found herein. By this book, read it, and most importantly, live it. Okay. So, where is it? I think this one, right? Read Stephens and Rango. Okay. SR05. This one. Okay, we are into the homework again. On fork.py, a simple process creation simulator that shows how processes are related in a single familiar tree. A simple process creation simulator that shows how processes are related in a single familiar tree. Read the relevant readme for details about how to run the simulator. Okay, let me check. Okay, step homework. Okay, I think it was in CPU API. Network TRL is CPU API. Okay, repeat this one. You know what? I would like to read the source code itself. Okay, random. Okay. Oh, for girl. Okay, so we initialize this one. Root name. Okay. Alright. Grow name. What grow name is? We are appending the name from the current name, I guess. So maybe I'm assuming that this one adding the current name and the base name. What is okay? How does this work? And what is the current name? Oh, is it a string? Okay. And you know what? Let me try. Say P1. Okay, right? And then P2. No, P1 plus P2. Okay. So we are combining names. The current names with the base name. Maybe something like that. Like adding a suffix, maybe. But yeah, we are combining the string there, I assume, and then we replace the current name with the new names. What the index is, I am not sure. And then we get name. Okay. Oh, okay. So if current index is the same as the what is it called? The length of the current name, we grow the name. Okay. Current name. Oh. Current index. Okay, if we are at the end of the index, I'm assuming that, then we grow the name, and then we get the name at those index and then increase the index. Okay. What about if the current index more than 9? Not equal to 9. Isn't that gonna make this one get an error index out of bounds? Maybe. I am not sure what the expectation here. Okay, this is the walk. Basic, okay. So we have print style, okay. Fancy line, okay. Character, right. Page style, okay. Never more than 0, okay. Printing note is last. Okay, max. Return print 3. Oh, we are using it in here. Okay. To fork. I assume this is when we are forking the process. Correct children, okay. Oh, wait a minute. What is this collect children to? Is it for the children list? Maybe. Okay, to exit, remove the process from process list. Okay. If local repair, okay. Descendant. Oh, okay. Yeah, looks like something. What is it? Creating the children process list, the child process list, and then remove it. One of the usage. Okay. I'm assuming we are only removing one process from the list, and with this one, but yeah, I'm not really sure. Okay. Bad action, okay. Plus minus, okay. Alright. Okay, so this is the running process. Let's play it. Okay, done this. While action. Random, okay, for pen. Exit choice, okay. For A in action list. Alright. If self cell 3 action. Cell action, okay. Final process 3, okay, pin 3. Okay, here is the option. We have set again to start the random position, maybe. To random the start position, if I assume correctly. And then we have 4% of action that are forks not exceeds, okay, fork percentage, action list, instead of randomly generated one, okay, so we can randomize the action list. Then action number of fork or exit to 2, okay, so 3 not action. I'm assuming we are not executing that when we provide this one. But yeah, the default is false. Let's see. Okay. Print style. Okay. What is the default one? Fancy. Okay. This is the default print style. Final only, just your final state. If only. Local repair, okay. And then if process. I am assuming leave process in here means the child process. But yeah, I might be wrong. Local parent to local parent, and then compute. Okay. Is there any help to use this? Or step homework? Okay. API for right. What is going on? So we already running the program. Okay. Wait a minute. So 3. Option so 3, okay. Okay, this one. If self.solve. What is the solve? Okay, let me check the readme. Wait, there is different readme fog and readme 2. There are now two simulators related to this chapter. The first, Fog.py, is a simple tool to show what a process tree looks like when processes are created and destroyed. Read more about it here, okay. Readme fog. The second is a program, generator.py, that creates real C programs that use fog with an exit to show how fog works in running programs. Oh, so with generator.py, we create the C program that use fog with an exit. We generate the C. Is it the source code or the executable? I mean, if we are running this Python script, we are running in the Python virtual machine, right? So maybe we will take a look at that later on. But for now, let's check this one, the fog one. How many lines? Okay, 100. To run it just okay. What you'll see then is a list of actions, such as whether a process called fog to create another process or whether a process called exit to stop running. Each process that is running can have multiple children or none. Every process except the initial process, which we call A here for a simplicity, is a single parent. Thus all processes are related in a tree. Look at the initial process. We will call this tree the process tree, and understanding what it looks like as processes are created and destroyed is the point of this simple homework. This tree, the process tree, what it looks like as processes are created and destroyed. So the simulation is to check, is to understand, or is to check what it looks like when the process create and destroy. Okay, simple example. Okay, we are using the set flag here to 4. Okay, process 3. Wait a minute. Except the initial process. Oh, so A is the initial process. So this one, A is the initial process. Okay. Evokes B, process 3, evokes C. I mean, what is this question? To do we need to answer this question, or is this the, what is it called? The answer? I'm assuming we need to answer this question because we didn't provide the compute flag. Right? This one, compute answer for me. So if we, so if we, let's say, provide something like this, then this should be different, I assume. Let's find out. Right. This is the answer. Okay. Okay, so we need to answer this one, right? From the output, you can see two things. First, on the right is the initial state of the system. You can see it contains one process, A. Operating system often create one or a few initial process to get things going. On Unix, for example, the initial process is called init. Usually people call it the init system, which spawn other process as the system runs. Second, on the left, you can see a series of action listing in which various actions take place, and then a question is posed about the state of the process tree is at that point. So it is a question for us to answer or analyze. Maybe that's the word. Question for us to analyze, to solve. So our output is the C flag, right? Thing like this. As you can see, the expected tree that reset, shown left to right from a particular operation is shown now. After the first action evokes B, you see a very simple tree with A shown as B parent. After a few more forks, a call to exit is made by T. Call to exit made by T, which registers the tree. Finally, A is created in the final tree with A as a parent of B, C, and E as considered siblings as the final state. So this is the, what is it called? The leaf, or maybe the child process, right? If you're using the term parent and child for the process rather than the tree and leaf, maybe root to be precise. In a simplified mode, you can just test yourself by trying to write down the final process tree. In simplified mode, by trying to write down the final process tree. Oh, okay. That is what this F flag is about. Final only. Okay. Once again, you can use this C flag to compute the answer and see if you were right. In this case, you should be, because it's the same problem. Okay, other option, a number of options exists with the Fog Simulator, you can flip the question around with the testy flag, which allow you to view process to states and then guess what action must have taken place. Okay, so the reverse, not showing the action but showing the tree instead. Sorry, like this one, showing the tree but what is the action, maybe something like that. Right, this is the tree, this, and we need to guess what the action is. Okay, interesting. You can use different random set or just don't specify one to get different randomly generated sequence. You can change what percentage of action are fog versus exit with -f flag. Okay, percent of action that are fog, not exit. The fog percentage. You can specify. Okay, let me check. Oh, is it a float? Oh, this is a float. Okay. You can specify specific fog and exit sequence with the -a flag to have A fog B and B then fog C, C exit, and finally A fog D. Just type we saw flag C here to solve the problem too. Okay. Oh. Okay. I think. Sorry. Yeah, I only have plus and minus as the action. So if we, let's say, use asterisk, we will get an error, I assume. Yeah, bad action. This one, bad action must be plus or negative, and the negative one should not have the, what is it, the end character like this. I'm assuming. Okay, right? You can only show final output and see if you can guess the intermediate to get there with the -f flag. Okay, -f flag. Alright. I think that's what we do. Oh. Okay. Final process 3. Oh. Wait, is it? Oh, it is different. Okay. Finally, you can change the printing style of the tree with the -p flag. Not this one. Where is it? Right. We are using fancy currently. So So let's try using basic. Oh, this is the basic. Okay. What about line 1? Okay. And line 2? Okay. Alright. Okay. And see which actions are taken. Can you predict what process tree looks like at each step? Use the test flag to check your answer. There's some different random set or more action to get the hang of it. Okay. Well, I think maybe we should check this out on the next session. Yeah, like one session for dedicated for the homework, something like that. I think we are gonna have multiple sessions dedicated to the homework. You are to gain some familiarity with process management API about which you just read. The knowledge is even more fun than it sounds. You will in general be much better off if you find as much time as you can to read some code. Why not start now? Okay. Are we using what is it called? Are we using the generate.py script or just plain writing the C code? I'm not sure. Okay, one step at a time. Next time we will take a look at this simulation homework. Okay, that's it for now. Thank you for watching and see you next time. Bye bye.